Let's cut to the chase. As of July 4th, 2012, the Higgs boson is the last fundamental piece of the standard model of particle physics to be discovered experimentally. But you might ask, why was the Higgs boson included in the standard model alongside well-known particles like electrons and photons and quarks if it hadn't been discovered back then in the 1970s? Good question. There are two main reasons. First, just like the electron is an excitation in the electron field, the Higgs boson is simply a particle which is an excitation of the everywhere permeating Higgs field. The Higgs field, in turn, plays an integral role in our model for the weak nuclear force. In particular, the Higgs field helps explain why it's so weak. We'll talk more about this in a later video, but even though weak nuclear theory was confirmed in the 1980s, in the equations, the Higgs field is so inextricably jumbled with the weak force that until now we've been unable to confirm its actual and independent existence. The second reason to include the Higgs in the standard model is some jargony business about the Higgs field giving other particles mass. But why does stuff need to be given mass in the first place? Isn't mass just an intrinsic property of matter, like electric charge? Well, in particle physics, no. Remember that in the standard model, we first write down a mathematical ingredients list of all the particles that we think are in nature, and their properties. You can watch my Theory of Everything video for a quick refresher. We then run this list through a big fancy mathematical machine, which spits out equations that tell us how these particles behave. Except, if we try to include mass as a property for the particles on our ingredients list, the math machine breaks. Maybe mass was a poor choice. But most particles we observe in nature do have mass, so we have to figure out some clever way of using ingredients that will spit out mass in the final equations without it being an input. Kind of like how you can let yeast, sugar, and water ferment into alcohol that wasn't there to begin with. And as you may be thirstily anticipating, the solution is to toss a yeasty Higgs field in with the other ingredients of the standard model, so that when we let the math ferment, we get out particles that have mass. But this model also brews up something we didn't intend, a solitary Higgs particle, the infamous boson. And since the model works so well to explain everything else, we figured it was pretty likely that the lonely boson is right too. To summarize, the Higgs boson is a particle which is a leftover excitation of the Higgs field, which in turn was needed in the standard model to 1. Explain the weak nuclear force, and 2. Explain why any of the other particles have mass at all. However, the boson is the only bit of the Higgs field which is independently verifiable, precisely because the other bits are tangled up in the weak nuclear force and in giving particles mass. The fact that the Higgs boson is so independent from the rest of the standard model is why it's the last piece of the puzzle to be discovered. And if it turns out to be exactly what was predicted, the standard model will be complete. The only problem is that we know the standard model isn't a complete description of the universe. It entirely misses out on gravity, for example. So to physicists, it would be much more interesting and helpful if the Higgs boson turns out to be not quite what we expect. Then we might get a clue as to how to reach a deeper understanding of the universe. So even though we just made a discovery, we can't sit back and relax. We need a hint, Mr. Higgs.